So, good morning, good evening, good afternoon, wherever you are in the world tuning in to this online workshop. My name is Sonia Bacca, and I am the Deputy Director of the MITP. And today I have the honor to formally open this online workshop on quantum field theory at the boundary. Matthias Norbert is not available, so you get me to do that, and I'm very happy to be here with you. So on behalf of the entire MITP team, I would like to welcome you all. And I would like to especially thank the organizers, Christopher, Christian, Andrew, and Sylvia, for taking the initiative and taking the lead to organize this event. And of course, I would like to thank also every participant who is either giving a talk or asking questions. Everything matters to make a workshop successful. So we really would like to wish you a successful and productive workshop and to have as much discussion as possible. We are well trained with Zoom by now. I see the chat is being already used, but we should use it only for physics questions, please. And otherwise you can of course use your raise hand feature. But I guess the point is the more you discuss with each other in the discussion session, the more closer it gets to what it could have been an in-person event. Unfortunately, it's not yet possible, but soon it will be. At MITP as an institute, we are very much looking forward to 2022, where we plan to reopen and have an in-person event. So I guess I don't have to take it too long. I just wanted to say one thing. If out of your discussion, you have then projects that are born and then eventually make it to a paper, it would be nice if you could acknowledge MITP. For us, it's really useful to keep track of this because it's a way to measure the influence we can have on the community. So thank you very much. And without further ado, I think we can start the scientific program, and I would like to leave the floor to the organizers. Thank you very much.
Hi, thanks, Sonia. On behalf of the organizers, I just want to welcome everybody, the organizers being me, Chris, Sylvia, Luca, Domenico, Christian, and Matthew. And I just also want to remind everybody that, see if I can send this message. Yeah, I put in the chat the website link, the link for the Gather space where you can have some informal conversation, and also our Slack channel where you have other informal conversation. And then I also want to remind everybody that later today we'll have a poster session that'll be in the Gather space at 4:30 p.m. European time. And then Tuesday and Wednesday and Thursday we'll have discussion sessions. And so we ask everybody who's watching to come up with questions and ask them during the talks, and also come to the discussion sessions prepared to ask lots of questions. The speakers will be in the discussion sessions. And so with that, anyway, I should have said I'm Andy O'Bannon at the University of Southampton, one of the organizers. But you're not here to hear me, so I'll pass it over to Chris to introduce our speaker.
Thanks, Andy. It's a pleasure to be here organizing this conference. I'm looking forward to lots of nice talks, and well, time is passing. So let me introduce my my distinguished colleague, Nadav Drukker, here at King's College London. And who better to start out this workshop on boundaries in QFT than someone who's done a lot of important work over the years with Wilson lines. And today he's going to talk about some new work on some two-dimensional cousins, surface operators. So without further ado, here's Nadav Drukker, who's going to tell us about an invitation to surface operators in the 2,0 theory. So please take it away, Nadav.
Thank you, Chris, for the introduction, and thank you everybody for being here. It's a pleasure, and let's see if I can get it right. Yeah. So this is my talk, and it is based on these 4 papers that I wrote. It's working, yes. And it's a real pleasure to be at this workshop, and I want to thank the organizers, and I am really sorry that I cannot be in Mainz. Physically, I was there about 10 years ago and really enjoyed it, the cathedral and the museum, and those who speak German would know that my name is the Dutch misspelling of my spiritual ancestor, Gutenberg, because one of my ancestors must have been a printer, but we don't know who that was. But I assume that's why I was offered the first slot in this conference. Not really. But anyhow, I want to talk about surface operators, and in this talk, I will first discuss what are the surface operators in the n equal to theory, and I will give a slow introduction. And then I will talk about my most recent paper with Maxime Trepanier about BPS observables, and some of the calculations and some of these examples I'll have to go over very quickly. And when I prepared these slides, I thought that Maxime will be giving a poster session this afternoon, but I see that there was some confusion about that, and his poster didn't come in on time.
No,
So
it will be there. It's already up there now.
Ah, okay, very good. So I was so he will continue my talk on the poster session. Thank you, Andy. So I'm talking about the objects in the 2,0 theory in 6 dimensions. So this is a superconformal theory in 6 dimensions, and the things that are known about it are sometimes a bit indirect. So we know it from M-theory considerations that it should exist. And we know that it should exist for every ADE kind of algebra, and we usually talk about the A series, so some theories with an SUN structure. And there is no Lagrangian for these theories, but the cases that we can study is the U1 case, which is essentially just a free tensor multiplet where we have the equations of motion. And in the large n limit, there is the M-theory description in ADS7 cross S4, the holographic large n dual. Now, this is famous that when we compactify it to 5 dimensions, we get 5-dimensional super Mills, and when we compactify it to 4 dimensions, we get if we preserve n equal 2 supersymmetry, we get class S theories. If we preserve n equals 4 supersymmetry, we get n equals 4 super Mills. So this, in some sense, is the mother of all supersymmetric theories, and at least many of them, and we want tools to understand these theories because there is no Lagrangian. So the simplest observable in these theories are surface operators, the most natural ones. And the way you can see it is that if we think of the 2,0 theory arising from M5 branes, then M-theory also has M2 branes that can end on the M5 brane, and the intersection between them is 2-dimensional. So we get a 2-dimensional object in 6 dimensions. These are the surface operators, and we can view them either as dynamical objects or as observables. Today, I will look only at the observables, so we fix the geometry completely. It's not a dynamical string. So when we compactify M-theory, if the M2 brane wraps a compact cycle, then it becomes a fundamental string, and the fundamental string ending on an M5 brane becomes an M2 brane becomes a fundamental string ending on a D brane, and fundamental string carry electric charge, and they can be either a particle or a Wilson loop, again, depending whether we look at a dynamical object or an observable. So the point of view is that surface operators are the Wilson loops, are the analog of Wilson loops and gauge theories to this theory. And since I love working on Wilson loops, I thought I should go work on surface operators in these in the 6D theory. So what should I tell you about Wilson loops? Why are Wilson loops so good? So they are very important observables in gauge theories. If we have a theory where we want to probe its phases, we can see if it's confining based on the behavior of the Wilson loops. And if we have a supersymmetry, Wilson loops are in many ways ideal observables. We can calculate them in many different ways using perturbation theory, using the ADS-CFT correspondence. We can use integrability. There are relations to scattering amplitudes. We can use localization to calculate the circular Wilson loop and other properly chosen Wilson loops. And we can use defect CFT techniques. And there are many talks and posters about defect CFT techniques for line operators. And so many of these, so it's an ideal tool where a lot of the ways you can study n equals 4 super-Yang mills apply. And in some cases, for example, in integrability and defect CFT, it is easier to study them for Wilson loops rather than for local operators or bulk observables. So in that way, I want to ask whether any of these tools will be applicable in 6D. So some of them are, and some of them aren't, and some of them we don't necessarily know. So there is no perturbation theory if you don't have a Lagrangian and you don't have a continuous coupling constant. There is ADS-CFT, so we can use that. We don't know how to use integrability in 6D. We don't know of scattering amplitudes. There is a hope that we could calculate some things exactly. And Maxime may talk about it in his poster, but it's still not really properly using localization because localization relies on a Lagrangian. And we can use defect CFT techniques because we can choose surfaces that preserve a subgroup of the conformal group and study operators living on them. And I will discuss some of that soon. So to give you an idea of what surface operators are, we can start with a free theory. So this is for just the U1 theory. And we have the theory has a 2 form and 5 scalars and some fermions, and we can construct an observable, which is the integral of this combination of the 2 form and of the scalars. And we exponentiate it, and this is similar to a Wilson line in Maxwell theory. We cannot do this for the non-abelian theory, first because we don't have any fields, and secondly because we don't have anything analogous to path ordering. But in all the rest of the discussion, we will rely on algebra and symmetries, and they are similar for the free theory as for the non-abelian theories. If we take a plane or a spherical surface and we take n, this vector here, 5 vector here, n, to be of length 1 and a constant, then it's easy to check that the supersymmetry variation of this vanishes for half of the supercharges. So this will be globally BPS. And we will name surfaces where n equals 1 but is not constant, or do not have the shape of a plane or a sphere, as locally BPS. It's just a name that we give them. So this is the one description, the one setup where we have an explicit description. The other setup is in a holography, where Maldacena told us that this theory should be dual to ADS 7 cross S4. And he also told us that the surface operators, also sometimes referred to as Wilson surface operators, should be described by an M2 brane in ADS 7 cross S4. An M2 brane has a 3-dimensional world volume, and it meets the boundary of ADS 7 at a 2-dimensional surface, which is where our surface operator is. And if we are lucky, we can solve for the minimal volume of this 3 surface, and then we get the leading large N result for the expectation value of this surface operator. As I will discuss soon, there is something that you can get from the near boundary analysis without solving globally the equations of motion. So this is the boundary conditions inside ADS 7. For S4, the boundary conditions are determined by this vector Ni. If it's of modulus 1, then we get Dirichlet boundary condition on S4. If mod n is equal to 0, then our M2 brane will satisfy Neumann boundary conditions. It won't be localized on S4. It will be smeared on it. Any questions about the background before I get into the first calculation? Okay. So the most common thing, and the first thing we need to ask about surface operators are what are their anomalies. And remember that when you look at local operators, you can get logarithmic divergences which account for their anomalous dimensions. So a local operator can have a dimension, a classical dimension, and then can have anomalous dimensions. Line operators usually have finite expectation values and no anomalies. But if they have a cusp, then they have mark point along them, there is an anomaly. And likewise, surface operators are 2-dimensional, and there are again logarithmic divergences in any calculation that you do, almost always, and these are called the anomalies. And so if we define our surface operator as V, and this is its expectation value, and we take the log of that, then any kind of calculation will give us some kind of log epsilon, where epsilon is a UV cutoff. And then we have an integral over a local quantity, which is here, which is known as the anomaly density. And this is related to some geometric quantity. So this is the Ricci scalar on the surface. This is the mean curvature squared. This is the pullback of the Schouten tensor. This is the pullback of the Weil tensor in the bulk. And this is the derivative of this scalar n. And you have these anomaly coefficients A1, A2, B, and C. So here we have a 2-dimensional surface, and if we were studying 2-dimensional CFT rather than an object in 6 dimension, the term you would have is this. Would be the usual central charge of your 2-dimensional CFT. But here we don't have a real 2-dimensional CFT. We have a 2-dimensional object in 6 dimensions, and there are also things related to the extrinsic curvature and the curvature in the bulk, especially the Weil tensor, and this extra couplings. Now, the way you should think about it is that, you know, you can take a surface of arbitrary geometry, which will determine all of these quantities. And your surface will have some intrinsic properties, which will tell you what kind of surface it is. And these will determine these four numbers, A1, A2, B, and C. And I should mention that in different papers on the topics, different bases are used for these anomaly coefficients, which is quite confusing, but in some places it's written very organized, so you can make the translations between the bases. So why do I call this an anomaly? So if I do a conformal transformation, that I can reabsorb it into a scaling of epsilon, and so the expectation value is not invariant under a conformal transformation, but transforms according to how these objects transform. In particular, if I choose my geometry to be a sphere of radius r in flat space, this term goes away, and I also ignore this term. For a sphere, of course, the Ricci scalar is different from 0, and in this basis, also this extrinsic curvature term doesn't vanish. There are other bases where you can move all of it together. And then you will get a contribution from A1 and A2, and you will get this behavior. I want to make the analogy to local operators, where instead of S2, you can think of an S0. S0 is 2 points, and indeed the 2-point function of two local operators is given by some distance to some power, which is the dimension of these operators. So in this case, I'm going to think of this 2A1 plus 4A2 as the dimension of my sphere. And then, so in these theory, in the 2,0 theory, the surfaces are classified by representations of SUN. In other theories where you have surface operators, there may be a different classification. Still, this formula would be always correct, with these numbers dependent on your theory and on the particular choice of type of surface operator. We are used to the dimension of a local operator to have a classical value and then quantum corrections. And likewise, our surface operators will have a classical value and then subleading terms at large n. Of course, again, this theory does not have a continuous coupling constant, so we will not have as complicated a dependence actually on the coupling as you would usually get for anomalous dimensions of local operators, say in n equals 4 super-Young Mills. So the calculation of it in the free theory was first done by these people and later repeated and slightly refined by my students and me. And what we do is we start with a surface operator that I wrote before and expand to quadratic order and just calculate free propagators, which again, we don't have a Lagrangian, so we don't have properly a propagator, but we can determine these, for example, by a conformal invariance and supersymmetry and so on. And then in order to deal with the divergences, one thing that we did in the paper that generalized what was previously done was to allow for arbitrary shapes of these surfaces and an arbitrary regularization by displacing, taking the surface, and we actually will have here, when we expand to quadratic order, I'm going to have two copies of it. So we have one phi will be living on sigma, and the other phi will be living on sigma shifted by vector field eta in some arbitrary direction. Sorry, a distance eta along a normal vector field v and u. And then you can do the calculation of this quantity integrated over the surface and this quantity integrated twice over the surface. And you get these contributions with 1 over epsilon squared here, which cancels when you have this relative I between these terms. Then you have a term that depends on your choice of vector field, but that exactly cancels. Anyhow, you would naturally just throw away a linear divergences, and quadratic divergences. You don't really care about power law divergences, but you don't even have to do that here. They cancel completely automatically. And then you get these contributions, which are logarithmic. They do not depend on the vector field, even separately, even if you don't include this term. And just from the 2 form, you'll get this term. And the logarithmic piece does not depend on the vector field. But of course, when you combine them together, you will get a formula like this. And now you see that this is the same formula as I had before, but the numbers in front, I don't have A1, A2, and C. They took particular values, and that tells me that A1 in this case is 1, A2 is -1, and C is 1. I was working in flat space, so I couldn't calculate B. So this is how I calculate the anomaly coefficients in the free theory. And then we can go to the holographic calculation. And this was done by Graham and Witten, and we generalized it slightly to add this parameter C. And this is what I referred to earlier, that you don't solve, you need to solve for the M2 brane equations of motion in ADS5 and ADS7 cross S4, but you don't solve them globally, you just solve the near boundary behavior using the Graham-Schmidt. The Graham okay, forgot the name, expansion, and you find the result that A1 is 0 at order n, A2 is -n, B is 0, and C is +n. And what you find is, if you compare them, both at in the free theory and at large n, you have that A2 is equal to -c. And this I will describe soon how we prove. But actually, a lot more is known from other calculations on the values of A1 and A2. And here I write their exact expressions for all n. And this took many, many, many years and many papers, especially by these people combined here together, to find what these functions are. So this agrees to leading order in n, so this is finite, so this is why there is no term proportional to n. This is a piece of ceramic that I tried to do to represent this, and some of the formulas for the ADS calculation and the field theory calculation are here. Here, for example, is the 2-point function of the B field. So let me tell you how we can prove this relation between A2 and C using defect CFT. And I probably should not be explaining to people at this conference what a defect CFT is, but since I'm the first speaker, I guess I still should go over it quickly. So if we have a CFT in capital D dimensions, and we have a flat or spherical defect of dimension little d, it breaks the symmetry to this subgroup, which still includes a conformal part, which in the case of a local operator, little d equals 0, this non-compact part is just dilations. And if D is equal to D minus 1, a boundary, as the name of this workshop is, then it will preserve just a one-dimensionless conformal group. And local operators localized on this submanifold will still be classified by representations of these subgroups. So either anomalous dimensions, well, dimensions of the dilatation operator, or representation of the subgroup, or any of these subgroups. And the nice thing is that some of the properties of CFTs still reduced to this defect CFTs, for example, the two-point functions of insertions into a defect, into a conformal defect, still obey this two-point function relation. The simplest object that exists in every defect CFT is the displacement operator that represents the breaking of translation invariance in the presence of the defect. So if this is the energy momentum tensor, its divergence is no longer zero. There is a term localized on the defect, and it's a vector quantity. And this is an operator in the defect CFT. Does not exist in the bulk, it only exists on the surface itself. And we can calculate its two-point function, and the dimension is d plus 1, and this should be n prime and n prime. And this is the, because it's derived from the energy momentum tensor, whose normalization is well defined, the normalization of these operators is fixed and is related to this CD, which in the case of Wilson loop is also related to the radiation of an accelerated particle, the Bremsstrahlung function. In any case, in this, I have the primes correctly. This is the case in a surface operator. We will have this dimension. D is 2, little d is 2, so d plus 1 is 3, 2, d plus 1 is 6. And this is the result from my paper, again, with another paper with Maxime and Malte, but it's really based on the idea developed in these papers for Wilson lines in 4 dimensions and for surface operators in 4 dimensions. And the point is that if you want to calculate, if you take a surface that is close to a plane, you can think about it as having some insertions of these displacements, and you can evaluate it to quadratic order. So I have any number of displacements, but I evaluate the quadratic order, and what I get for the expectation value of the surface operator at this order would just be the integrated two-point function of these displacements with the degree of displacement that I displaced my surface, how far it is from the plane. And now I can calculate this thing. Of course, this will give me a CD, and then I will have this, this distance sigma, which here I translate to eta, particular direction, size, and you do this integral, and you have some power law divergences, but then you also have logarithmic divergences, and they end up being proportional to CD, of course, because I had CD here with some numerical coefficients. And this quantity in the geometry, once you integrate this by parts, you get from here to here, you get derivatives of these vector fields, which translate into derivatives of the shape of the surface, which are captured by this extrinsic curvature. So they are related to the anomaly coefficients A2. And you find a relation between A2 and CD. But then you can also, in addition to the energy momentum tensor in the supersymmetric theory, you also have the R symmetry for SO5 R symmetry, and you also have the supercurrent, and you have the similar operators related to their breaking. So you have sort of a scalar-like displacement. That's what happens if you change the scalar coupling. And this two-point function of these O's would give you a coefficient CO, which is again completely determined. And then by repeating the calculation in the last slide, you can find the anomaly coefficient little c is exactly equal to this CO. And then you can use supersymmetry to relate this, this, and this. So so D is a descendant of O. So that fixes a relation between CD and CO, as so. And this fixes a relation between little c and A2. So that proves that relationship. Okay, it's a good time to pause again and ask if there are any questions.
Yeah, Nadav, so you mentioned, well, maybe I missed it, maybe I misunderstood, but you mentioned something about D equals 1 and D equals 2 defect CFT having Virasoro. So in general, I guess that's not really true.
No, I mentioned capital D having capital
okay.
D has 1 or 2. Sorry, my slides. If the bulk.
So this is about bulk. Oh, good. Okay, so you obviously you never used Virasoro or anything in any of this discussion, I guess.
No, certainly.
Okay, good. Okay, thanks. Yeah.
No, thanks for the question. Sorry if I was unclear. I didn't mention it. Yeah, it was just on the slide. So. Any other questions?
I just wanted to say, Nadav, you have about 10 minutes left.
Including all the long introductions?
7 minutes, yeah, extra.
Okay. So, okay, so here I get to my most recent paper with Maxime from last year. You can see that the 4 papers I had at the beginning are grouped 2 in the first lockdown, 2 in the second wave, and we have a few papers that are waiting for the next wave to be published. And so this one is from the peak of the second wave. And what we are looking at are surfaces that preserve some global symmetry. So the discussion I had so far, the symmetric one, the defect CFT, is designed around the half BPS plane or sphere, but the anomaly calculation, you can do it for a surface of any of arbitrary geometry, and scalar coupling does not have to be supersymmetric. But our theory has 32 supercharges. Locally BPS one has a half rank projector at every point. But you have this same kind of another one of these equations at every point along the surface, and generally for more than one half rank projector equation, you won't have any non-trivial solutions. But we want to find a way to find compatible equations at all points along the surface. The simplest case is the plane, where all the equations are going to be identical, and that is globally 1/2 BPS. But if we want to find cases with less supersymmetry, then we found 4 classes and a bunch of subclasses, which we call type R, type C, type H, type S. And I will describe their geometry in a bit. And holographically, each of them is related to some generalized calibrating forms in a subspace, appropriate subspace of ADS7 cross S4. So start with type R. And in this case, what I do is I consider a plane, a surface that is extended along the x6 direction. And in the transverse R5, it can take an arbitrary, it will be an arbitrary curve. So I have a x of u, u is one of my world volume coordinate inside R5, and then x6 is equal to my second world volume coordinate. And I choose my scalar coupling to only depend on xi. So it does not depend really on v. Now, if inside R5 I only have an R, then that is a plane. If I have a curve inside R, which is of this shape, it's a cusp, then what I'm actually describing is a crease, a folded piece of paper. Sorry, that's this. And if you're familiar with supersymmetric Wilson loops, this is an obvious uplift of the Zaremba Wilson loops in 4 dimensions. If you calculate the anomaly of those, it exactly cancels between the n and the x part, the extrinsic curvature part, and the scalar part, because a2 is equal to minus c. There's no anomaly, and we think that also the expectation value vanishes. But it's also extensive in this infinite direction, so sort of has to. So that's a simple case. Another case is to view R6, where our theory lives, as a complex manifold, and fix the scalar coupling to be just in the direction 5, for example. And then for any holomorphic surface, holomorphic curve inside C3, our surface will preserve 2 supercharges. If we restrict it to be in a 4-dimensional subspace in C2, it will preserve 4. Of course, if we restrict it to C, we get the plane again. Now, if you calculate this the anomaly of it, what you find is actually the Euler character of this surface. And it's easy to construct the holographic duals of these type. So we find here some example with complex geometry. Then there is a case with the most rich case is actually when we restrict our surfaces to be inside an R4. And now we allow them to take any shape. They don't have to be holomorphic or anything like that. They can be any shape inside R4, as long as the scalar coupling is taken to be this. So this is the derivative of these 2 coordinates with respect to A and B, the worldsheet coordinates contracted with epsilon, and eta is the 't Hooft symbol. And generally, they preserve just 1 single supercharge. If you restrict instead of R4 to R3, they will preserve 2 supercharges. If inside R4, they are Lagrangian submanifolds with respect to usual symplectic form, then this one will become, you're just going to take 2 values instead of taking 3 values. So it will be inside a circle. And again, it will preserve 2 supercharges. These are related in some way, in some cases. I mean, there is similarity here to the construction of DGRT Wilson loops. And there is a particular relation in some cases. In other cases, it's a more abstract relation. And this quantity is actually related to what's known as the Gauss map. And the anomaly is related to the degree of the Gauss map. So it has some topological meaning. And holographically, we can describe them in terms of surfaces calibrated with respect to a G2 structure, an almost G2 structure, and ADS5 cross S2 subspace of ADS7 cross S4. So there's a very rich structure here. We don't have many explicit examples. We have some explicit examples that we can study. We can find the solutions in holography but we know a lot of the properties regardless, just by supersymmetry and so on. And the last case is type S, which also has some similarities to the DGRT Wilson loops. In this case, the scalar couplings are related by an epsilon tensor. And now, so we're inside a sphere. So X has size 1. So we have X, partial X, and partial X. We can track them with a 4 tensor of SO4 of the symmetry of S3 and a 2 tensor on the world volume. And these will generally preserve combinations of Q and S. And so they're, again, similar in some ways to the DGRT Wilson loops. And the anomaly is complicated, actually is proportional to the volume of the surface inside S2, which is very confusing because you wouldn't, that seems to break conformal invariance. But of course, here I assumed a radius 1 sphere. And you should, if you take a different size sphere, you should divide here by r squared, and then it is a conformal invariant quantity. So there is something here related to the Euler character and something related to the volume. And here is another plot that I made inspired by curvy surface inside S3, but it's really more close in S2. So to start to conclude, this is a summary of these examples that I found in type R, type C, type H, and type S, and there are restrictions if you're Lagrangian or if you're in a 3-dimensional submanifold, and the number of supercharges and the anomalies, intersections between them, and so on. Here, if you have a curve inside R5, 1 supercharge, inside R4, 1 supercharge, R3, 2 supercharges, and so on. And then there are extra special cases inside them with extra symmetries, like if you take a cone or a crease. These can exist in these different types and have varying degrees of supersymmetry. You can take a torus, which is naturally Lagrangian, if it's inside this space, so on. And you can construct all kinds of spheres, latitudes, a large sphere, and so on. So there are all kinds of special examples, and we say in our paper, we say a little bit about them, but there is still a lot to uncover about them. So to conclude, in this invitation to surface operators, I try to explain why they are nice and natural observables of the 6D theory, and a way that we can have a handle on it. We have a lot of results on them. We know their anomalies. We know classifications of BPS operators and so on. They are similar to Wilson loops, so we hope to be able to say many things about them. And some of the things we know about Wilson loops apply in that case. And this I already said. So as outlook, when we talk about surface operators, normally we discuss the anomalies. And there are logarithmic divergences, and these are the anomalies. And we should think about them as as analogous to classical dimensions, one loop anomalous dimensions, and 2 loop anomalous dimensions. But we actually know them in the 2,0 theory. But even if we don't know them, when we have local operators that have classical or anomalous dimensions, we still know how to do calculations with them. And we don't only ask what are their dimensions. So in particular, what we ask about local operators, what are their structure constants? And of course, when you define a structure constant of a local operator that has anomalous dimensions, you need to take into account that it is anomalous, and you need to define it properly such that you get a finite a structure constant. And we are now at the stage that we can start defining finite quantities also for surface operators that are anomalous. It's not exactly the same as a 3-point function, but if you will go to the poster section and talk to Maxime, he will explain to you how we calculate a quantity which is related to a surface which is made out of 2 hemispheres. So if you take a hemisphere and you glue it to another hemisphere, but such that here there is an angle, it's not really 2 hemispheres. So topologically, it's still a sphere, but geometrically, it's not exactly a sphere. And the curvature everywhere is the same as on a sphere, except this fold on the crease, but that doesn't contribute to the anomaly. And therefore, we can calculate all of these objects, regardless of the angle, have the same anomaly, and therefore we can calculate the ratio between them, and that gives us finite quantities, and we have some nice results for that. So I should finish. Thank you.
Thanks very much, Nadav. Are there questions? I had one, which was whether you could say a little bit more about these this vector n quantity and how it comes out. I guess I understood it came from the fact that you have a supersymmetric system, and like what happens if it isn't supersymmetric, or if there's more or less supersymmetry. Is there? Can you flesh out a little bit more there?
Yeah, so it arose naturally. Oh, sorry about this. It arose naturally because we had a scalar in the free field realization. We can see it just because we have these scalars. So if you're familiar with the Wilson loops in a n=4 superennials, there is a similar kind of coupling, and here I'm doing the same thing. The fact that these are superpartners of B is not really crucial for this story. So if you take a theory where you have you have a 2 form that you want to integrate, but even if you don't have a 2 form and you just have scalars, you can define a surface operator just based on this. And if you have a theory with just scalars, you can define a surface operator just by integrating them. And then you have these quantities n. So if we go to the anomaly story here, it's not universal. This is sorry, it's taking time to catch up. This is not universal. This is related to this particular theory that we get this quantity. But in other theories, you can think of this as coupling to some extra degrees of freedom. You can get terms like this by coupling to some global symmetries. If you could, yeah, in this case, the global symmetry is an R symmetry, but in principle, if your surface couples to global symmetries, you can have these extra terms. I'm not sure if I answered your question.
That's fine. Yeah, I just wanted a few more. I mean, I'm just used to thinking only about the purely metric contributions to the anomaly in this business.
I have a question, if I can.
Please.
Do we still have time? Yes. Hi, Nadav. Nice, very, very nice talk, great talk. So my question concerns in particular, the calculation of anomalies. So the impression is that even if you do not know the Lagrangian of the theory, you are assuming that the Lagrangian is somehow a smooth deformation of the free Lagrangian. Is that correct?
I'm not assuming anything about any Lagrangian.
Well, but when you expand, when you write your result, where there are plus dots, what are the dots? I mean, when you are using free propagators. So basically, you are assuming that there is some limit with. Yeah,
here
dots there in your equations. Dots stay for what? Yeah, those ones.
Is subleading terms in epsilon, finite in epsilon, or linear in epsilon?
Yeah, but this is probably the quadratic term in the expansion.
No. Well, I'm. All of this is just reliant on that.
But when you have the exponential of your integral, what do you do with the exponential? You expand, I guess.
Well, it's a free. This is free, so
you just expand, and then
I just expand, and if I have higher powers, it's still just given by free contractions. So whatever I get from quadratic, it's like in any free theory. Whatever I get in quadratic order just exponentiates. I don't need to worry about higher orders in this expansion because it is a free theory. This is just higher orders in epsilon, not higher orders in fields.
Yeah.
But everything higher order in fields is just captured by this. So this is just the log. The log of this is exactly that plus higher order in epsilon. Nothing from higher order in the fields. Okay,
maybe we can discuss tomorrow at the discussion session. I still have some doubts, but we better stop here. Thanks a lot.
Yeah, I think we should probably stop here.